We looked at the algebra. We looked at numbers. So now, the heart of the maths, the functions themselves that we work with. So some definitions to start off with. A relation. So a relation is simply a rule that maps between two sets of values. Something like that. Okay, so one set of called the x values, one set of called the y values, and we can see arrows going in either direction, they map to each other. That obeys the relationship x squared plus y squared equals 5. A function is a special type of relation. It uniquely maps from one set of values to another set of values, so it's unique. So something like that. That one would be y equals x squared. But you'll notice the difference here that the arrows are going in one direction because every x value goes to a y value, but each y value can come from more than one x value. But an x value can only go to one y value. Independent variable, that's like the input of the function. What we tend to use as x values in our equation. It doesn't have to be x values, but the independent variable. Domain is every possible value that can be substituted into the function and get an answer. That's every possibility. Now sometimes we have to restrict the domain. So an example I've got here is if we were talking about time, the represented time, we'd probably restrict the variable to be t is greater than or equal to 0, because we don't really talk about negative time. So you might have some restriction on there. Dependent variable then becomes the output. So why are they called independent and dependent? Well, independent because it's free choice. Pick any value you like. But then the y value, or the output, depends upon which value you picked. So it becomes the dependent variable. Range is then all the possible answers, all the possibilities that the dependent variable can take. You always put the independent variable on a graph on the horizontal axis and the dependent variable on the vertical axis. And that's why the horizontal one is the x-axis and the vertical one is the y-axis. And in science, you might have noticed that as well. When you're doing experiments, you usually would put time on the horizontal axis because that tends to be the independent variable. And then whatever you're measuring, velocity, whatever it is, tends to go on the vertical axis because it depends upon the time. Function notation then. It's just this idea. F, it doesn't have to be F, you can use any letter you like. It's probably more these parentheses. So we're saying y is some function of x. We're going to substitute x values into this thing and get answers out for y. The independent variable goes inside the function, and so f's representing the function, and the dependent variable is the answer that it then gets. Simple little example, let's say function x is 3x squared plus 4, then function 5, well, substitute in 5, what do we get? 79 would be the output. It doesn't have to be a number, you could put in a pronumeron, it looks silly, but function a, all it's really saying is, well, everywhere you see an x, let's replace it with an a. So it becomes 3a squared plus 4. Of course, it doesn't have to be a single pronumeral, you could do something like this. And this will become very important later on, but function x plus h minus function x. So first of all, wherever we see an x, we're going to replace it with x plus h. So we get 3x plus h squared plus 4, but then we're going to subtract function x as well. So subtract the 3x squared plus 4, expand it out, collect like terms, we end up with 6xh plus 3h squared. So how can I tell whether a relation is indeed a function? Now visually is probably the easiest way, and that's what we call the vertical line test. If you draw a straight line parallel to the y-axis, so in other words it's vertical, then it will only cross a function once, if at all. Because that's what we said. We said the next value can only go to one y value. So visually, very easy to tell whether something is a function. So there's the hyperbola I was just talking about. Doesn't matter where I put that vertical line, it will only cut it a maximum of once. So yeah, that's a function. As opposed to a parabola on its sides, that would be x equals y squared. No good, because look, I can draw a vertical line and it cuts it twice. No. Not a function, that's just a relation. What it actually is, something like this, is actually two different functions that have been joined together. Y equals the positive square root of x, which is the top half of the parabola, and y equals the negative square root of x, which is the bottom half of the parabola there. So domain and range, that's telling us what numbers are in these sets that we're talking about. So how do you find a domain? There's some key things to look for. Now, geometrically, you could just look at the picture and go, oh yeah, I can see what x values are giving me an answer. So there's x equals y squared. What would its domain be? I always think, I'm just imagining that I'm walking along the x-axis and I look up and look down and do I see the function? If I do, then it's part of the domain. If I don't, then it's not. So for this one, I'm walking along, oh, no, negatives, no, nothing here, nothing here. Oh, I hit 0, whoa, hey, there's a curve, what's going on? Go past, oh yeah, there's something above me, there's something below me. So the domain for this would be x is greater than or equal to 0. Any value in that would give us an answer. One of these split functions, again, if you start walking along, we end up with x is less than or equal to 0, but then there's a gap, it jumps, and it doesn't reappear until we get to 2. Now 2 is not included in this one because we've got the hollow circle, so it would just be x is greater than 2. That would be its domain. So fantastic if we can see the picture. If we recognise the equation, we can draw ourselves a sketch, we can get the domain very quick. But maybe you don't recognise it, so what should we be looking out for? Fractions. Okay, let's think about fractions. Key things we know about fractions. We know the bottom of a fraction can't equal 0. So if I have this, and let's pretend I have no idea what this looks like. What's its domain? Well, I know the bottom of this fraction can't equal 0. So I know x can't equal 0. But I could substitute anything else I like in there. The way we would express this, we say, well, it's all real x. I could substitute in any real number I like, except x equals 0. I can't sub that one in. So that's one way of saying all real x except x equals 0. Some people write it as all real x except x cannot equal 0. I guess we're just playing with semantics, because if you think about it, I could say all real x except x equals 0. But then someone else could say, oh, all real x except x can't equal 0. You get away with it either way. At least you're pointing out there's a problem at 0. Well, y equals 1 on x squared minus 1. I still ask myself the same question. Well, the bottom of the fraction can't equal 0, so where's my problem? Well, x squared can't equal 1. So in this case, there's 2 points excluded from the domain. X can't equal plus or minus 1. So that one's going to be all real x, except x can't equal plus or minus 1. Oh, 2 fractions. Well, rule's still the same for both fractions. So I know x minus 1 can't equal 0. That gives me 1 point that's missing from the domain. And 7 minus x can't equal 0. So there's another point that can't be in the domain. So alright, all real x, anything else I can substitute in? No, I just can't substitute in 1 or 7. When you're mentioning all real x, it's important you say x, because you're letting them know that the domain is about the x values. Don't just say all real, because all real what? X or y? You're not telling me. It's the x values here. Square root signs. Well, not just square roots, I suppose any even root. But root signs, we know we can't find the square root of a negative number. So this could cause problems as well. Y equals the square root of 4 minus x squared. Now you may or may not recognise what that is straight away. But let's say we don't. I know that that's got to be a positive number, because I can't find the square root of a negative number, or equal to 0, I guess. Well, solving that, I'll get x squared is less than or equal to 4, so x must be in between minus 2 and 2. So there's my domain. I can only substitute in values in between minus 2 and 2. 2 different square roots. Well, rules are still the same. So I know for the first square root sign, x has got to be greater than or equal to minus 3. For the second one, x has got to be less than or equal to 5. But both have to be true, because I've got to substitute in them both. So if I combine that together, I end up that I could only use values in between minus 3 and 5 and get an answer. 1 over the square root of x plus 2. So now I've got both situations. I've got a square root and I've got a fraction. What difference does that make? Well, all it really means is instead of going x plus 2 is greater than or equal to, it's just x plus 2 is greater than, because it can't equal, because you can't have 0 on the bottom of the fraction. So x plus 2 is greater than 0, x is greater than negative 2. So what about range? Again, geometrically, if you look at the picture, nice and easy. So this time we're climbing up the y-axis and asking where is the function. So for this one, if I was to climb up the y-axis, doesn't matter where I am, I'll look to the right and yep, there's the function. So we say all real y. Not just all reals, as I said before. We let them know it's the y values that are important here with the range. So all real y. That split function we looked at, well, this one, the y values will be less than or equal to 1, and then we've got y is greater than 3 as well. Don't recognise the picture? What do we look for here? What are the key things for range? Maximum and minimum values, because now we're talking about how high does the thing go? How far down does it go? We know that even powers, so squares to the power of 4, but also absolute values are always going to be greater than or equal to 0. It could only produce positive numbers. So if we see that, let's pick the most basic one, y equals x squared. Let's pretend we have no idea what this looks like. But hang on, x squared, that's got to be positive. Therefore, y's got to be positive. So the range is y is greater than or equal to 0. I'm only ever going to get answers that are greater than or equal to 0. So if I had x squared plus 3, well, I know the x squared's got to be greater than or equal to 0. So this one's range will be greater than or equal to 0 plus 3, which is greater than or equal to 3. 5 minus x squared. Here's where we've got to be careful because of the negative. If the smallest x squared can be is 0, then when I make it negative, it's like turning it upside down. Now we're talking about the biggest it could be would be 0. So the biggest it could be was 0, so therefore the biggest y could be would be 5 minus 0, which is of course 5. There's our range. Absolute value of x plus 2. Absolute value has to be a positive. So y has to be greater than or equal to 0. Absolute value of x plus 2 minus 5. So similar to the second example where we've added a number, well in this case we're subtracting a number. So y is going to be greater than or equal to 0 minus 5. Y is greater than or equal to minus 5. The other thing that sometimes happens is if we have a restriction on the domain. So we found our domain, but there were points that couldn't be included. There was some sort of restriction. Well, that's going to affect the range, possibly. How do we work it out? Here's the general idea. Sub in the endpoints of the domain. You'd be surprised how often these things are symmetric. So another good point to pick is maybe the centre of the domain as well. And it gets you a feel for, righto, I think this function's going between these values. So back to the square root of 4 minus x squared, we said the domain was in between minus 2 and 2. Well, if I sub in 2, I get the answer 0. I didn't bother with negative 2 because I'm squaring, so it's going to give the same answer anyway. Sub in 0, I get 2. So I'm pretty confident this range is going between 0 and 2. Fractions. What about fractions? If you've got a constant on the top of a fraction, then it would be impossible for that fraction to equal 0. Impossible. So therefore, when I see something like this, y equals 1 on x, I know that y can't equal 0. Impossible for that fraction to equal 0. So the range, therefore, is all real y, except y can't equal 0. There's no way it can equal 0. So get the idea of, right, just add to that. Well, then 5 plus 1 on x. I can't have 5 plus 0, because that fraction can't equal 0. So all real y, except y is 5. Not immediately obvious, this one. X plus 7 on x plus 4. So what I do is a division. You might remember polynomial divisions. I could rewrite that fraction 1 plus 3 on x plus 4. Now I've got a situation where I've got a fraction constant on the top. I know that can't equal 0. Therefore, y can't equal 1 plus 0. So there's the polynomial. I'm not saying you would do that necessarily, but if we did a polynomial division on that, it would look something like that. And so we see, oh yeah, it goes in at once with the remainder of 3. Hence we get 1 plus 3 on x plus 4. As I say, we can't get 1 plus 0 then. So it's all real y except y equals 1. Okay, that's enough for today. So 3a, 3b.